Hello. So in this video we are going to discuss the policy gradient methods and the policy gradient baseline. So in the policy gradient we will discuss reinforce, and in the policy gradient baseline we will discuss a special case of policy gradient baseline, which is critic. Policy gradient baseline. So, as we see in the DQN or double DQN or other algorithms, we use more than a network. Like in DQN, we use the policy network and the target network. In the policy gradient, we just use one network to get the predictions. So, for example, uh, we are going with our usual example, which is the self-driving car example, where we have three actions. Either we want to go left or straight or on the right. We just pass it an image at timestamp 0, and we will get the probabilities of each action, and based on those probabilities, uh, for example for the action 1 we get 0.6 probability. For the action 2 we get action 2 or going straight we get the 0.4 probability, and for the right action we get 0.1 0.3 and 0.1 probability. So let's suppose these are the probabilities. So if using the epsilon grid we are taking a random action, then action can be anything. Or if we are choosing the deterministic action, then we will choose the action with the highest probability. So in this case, let's suppose we are choosing this action, which is the left action. So before going to the training part, we will collect all the data. For example, current state and the action we chose, which in this case is the left, and the next state as dash, and reward on that next state. And we can also store the probability of the action that we just chose. For example, in this case, p dash. Implementation can be anything. It's just I'm explaining this just to give you an intuition of how things work. So let me give you so as we know that every neural network needs a loss function for the optimization. So in this case we will just use the reward as our loss with the probability term, which let me shade here. Mm, so here is the term. Let me copy it. So yes, this is the term. Copied. Okay, so here it is. Let me make it a little clear for you. So here we are multiplying the log or the log probabilities, which we can use, like here we have probability like it's 0.6, and the reward after taking this action we are just multiplying it with the reward, and this is kind of a loss function, and we will use its derivative for the updation of this network weights. So for example, uh, here the probability is 0.6, and we chose the left action. So 0.6 multiplied by its reward, which is for example 5, and for next timestamp the probability can be 0.1 multiplied by its reward, which can be 1, and so on. So this is our loss, and based on this loss we will update all the weights of this network, and that's how we will optimize our network to get better and better. So for your intuition, If reward is high, that means the action was good, so our network uh, will increase its probability. This is how the weights will be updated. These are the old weights, or old weights plus the learning rate and the loss term and its derivative. So that's how we will use gradient ascent term to update the weights. As we know that we are multiplying the reward here, so we do not want gradient descent here. If I mention gradient descent, then it's wrong. We will use gradient descent here. As we know, reward is higher. If the gradient descent was used, then rewards will be higher in the start, and with the gradient descent it will become low with time. But we do not want that. We want to increase our rewards, so we will use gradient descent. The intuition is, if the reward is high, action was good, we need to increase its probability, and that's how the network will adjust its weights to increase these probabilities. And if the reward is low, then the action was bad and we need to decrease its probability. But here's the problem: variance of this will be high. Why? Because rewards can be very high for some states and can be very low for some other states, so there will be a lot of fluctuation, so the updates will not be stable, and that's a problem here. So for to cater that, we will use policy gradient with baselines, policy gradient baseline. So let me copy. So now let's discuss policy gradient baseline methods, and we will discuss the special case of policy gradient, which is actor critic policy gradient baseline. In the policy gradient baseline, instead of directly multiplying RT with the log probabilities, we subtract a baseline term from reward, so which you can see here. Hmm. Yes, here it is. So instead of directly multiplying reward, the equation is same like the reinforced algorithm that we just discussed, but here is just additional term where we are subtracting the baseline term. Baseline term basically gives us the potential or the overall rewards of a specific state. We are passing a state and we are getting a scalar out of it. So if the RT is greater than the baseline term, then the action was better than average. Baseline term can be the value of a state, value of a specific state. So as we know, value is the overall potential of a specific state. So the reward, if the reward is greater than the overall or the average reward, then that means the action was better than average. So we need to increase its probability. And if the reward is less than the overall average, then we need to decrease this probability, as this is not a good action. So this will be our loss term, and here is the update equation where we are using gradient descent. Here this is just new term which is stabilizing the reward term, as in the policy gradient specifically reinforce it, it was causing the updates to fluctuate, but here we are subtracting the value term. This will stabilize the learning. So now the question is how we are gonna get this value term. So for the value term, we are, as I already talked about, that we will discuss a specific case of policy gradient baseline, which is actor critic. In the actor critic method, we have two networks. Actor critic. We have two networks. First network is to actually give us the action and its probability, and the other network will be to calculate the values. So now let's discuss the. So firstly, we need to collect the data, and the policy network will give us the probabilities, uh, and we will sample some actions, and after that we will use the value network to compute the baseline. Value network will give us how good a state is. So for example, if we are at timestamp 0 and we will pass that state, it will give us a scalar value of how good. Let's suppose it gives us a 5 value, it will tell us how good this state is. In the start it will give us a wrong value, but with time it will obviously improve, and we will see how it will improve. We will compute the advantage. So as we know that reward minus the value or the overall potential of a state, we can call it an advantage. So we will calculate the advantage RT minus VT, which will be used in the loss term. Then we will use this equation, or we will use this to find the gradients for the gradient descent, and we will update update the weights of the policy network. And after that we need to improve our value network too. As in the start it will give us the wrong values, but as we have the rewards of each state, then we just need to subtract our current value that we are getting from the network, which will be wrong in the start. We'll just subtract it from the actual rewards, and this is just a mean square error formula, and based on this loss we will use gradient descent to improve the value network, and that's how value network will be improved and the policy network will be improved. Both of networks will be trained simultaneously, and uh, this will cause or this will help us improve the problem of the instability in the policy gradient method. And that's all about the actor critic method and the policy gradient and the policy gradient baselines. Thank you.